My name is Xing Chen, and I will be presenting MetaWave, attacking mmWave sensing with metamaterial hashtags. This is a joint work with CU Denver, UC San Diego, SUNY Buffalo, the University of Edinburgh, and Zhejiang University. mmWave sensing has been intensively employed in many crucial applications such as automobile, security, and robotics. This is exceptional ability to determine the target's range, angle, and velocity. And it works in harsh weather and climate conditions. The mmWave radar are mainly used for optical detection, speed measurement, localization, and so on. Due to their widespread use, there are particular emphasis on investigating the different kind of attack on mmWave sensing and identify the solution to mitigate these attacks. The attacks on mmWave sensing can interfere or manipulate the sensing measurement results and makes the object disappear or just create a ghost objects, which can directly or indirectly cause serious consequences such as crash accident, malicious invasion, and sudden breaking. Existing attacks on mmWave sensing mainly relies on transmitters to actively shoot malicious signal or jam the signal at the target frequency. It not only requires a highly expensive and dedicated equipment, but also can be easily prevented by human inspection at the security checking. Therefore, we ask the question, is it possible to attack mmWave sensing positively? There are previous work demonstrated that it is possible to attack camera recognition system by simply putting some stickers on the object. So we wonder if it's possible to do that as well for mmWave sensing. To be more precise, here is an example. Imagine we have a roadblock in front of a self-driving vehicle, which is equipped with the mmWave radar. When the car is approaching to the roadblock, the radar will give an alert to the decision system and admit the car braking. But what if we can put some special stickers or tags on the roadblock that will make the radar think there's nothing ahead and keep the car moving? This may result in a severe crash accident. We formulate this kind of attack in our threat model. We consider an attacker E is trying to spoof the victim Bob, who's using mmWave sensing for measurement and detection on their vehicles. We assume there is a strict security check for any personnel entering this area. Therefore, any suspicious equipment such as RF transmitters will be prevented. We also assume that this is a well-controlled environment, so there's no way for the attacker to access or modify any hardware or the victim's vehicle. So we also consider it's a black box attack. Also, the attacker knows some physical property of the radar, such as frequency and bandwidth. They have no knowledge about the implementation of the actual sensing algorithm. Here we propose two types of attacks. The vanish attack, which can hide an optical that the victim Bob should avoid. The ghost attack is to make an object out of thin air and trigger the false alert for the optical detection. These two types of attacks can also be extended to other applications such as security monitoring and trespassing detection. We present our solution to this attack, MetaWave, using passive metamaterial attacks to attack mmWave sensing. However, that raises a question: how do we actually design and deploy these tags to adapt different scenarios and achieve the best attack performance? To solve this question, we propose a new attack system. The MetaWave attack system takes the description of the attack scenario and our attack goal as input. The system will automatically fine-tune attack design and the deployment instruction. The attacker can simply fabricate the tag and set up a trap according to these instructions. To begin with, we first categorize the metamaterial into three categories. The absorption tag is to largely attenuate the amplitude of the echo signal, which can make the sensor believe there is no object detected and make the object disappear. The reflection tag is to rebound the transmitted signal and spoof the object detection by overwhelming the object signal. The polarization tag is to restrict a specific field of the electromagnetic wave, which can tamper with the echo signal. We explored different kinds of tag design, including 2D and 3D tags. We finalized with the hexagon array since the orientation and material and so on of each hexagon can be individually adjusted to adapt different type of objects. We choose the urethane foam, tinfoil, and the copper wire as the metamaterial for the absorption, reflection, and polarization tags. The cost for each tag ranges from a few cents to a few dollars. This material are commercial off the shelf, which means they are very easily obtainable. To achieve MetaWave attack system, we first create a digital twin of the attack scenario according to the description. Attack design is also initialized in the digital twin as well and will be optimized. We designed and developed a differentiable radio frequency simulator, which can not only simulate the RF echo signal from a given 3D scene, but also it outputs the gradients with respect to each scene parameters, which can give us the direction for optimizing the scene toward our attack goal. Then we can use the MetaWave tag optimizer to perform a gradient descent and back propagate to the scene parameters. After several iterations of optimizations, the system will output the tag design and deployment parameter for the attacker. Here are an example of the description of a attack scenario in the digital twin. On the left side is the example of the scene parameter, which contains two parts. The victim parameter describes the specifications of the victim's radar, such as frequency, bandwidth, and so on. This parameter can be obtained from the radar manufacturer, the user venues. The trap parameter describes the optical and the surrounding environments, such as geometry, material property, and the locations. Those information can be obtained from using the camera and the reconstruction techniques such as neural reading field. On the right side is the parameter that describe the MetaWave tag. These are the parameters that will be optimized. The tag parameter include the tag material, pattern, size, location, and orientations. With this parameter, we can construct a digital twin and will have a closed loop in the digital twin. Here's an example. The MetaWave tag vanishes the roadblock and can lead to a severe collision on highways. The victim parameter are used to describe the victim sensor, and the trap parameter are used to describe the optical, in this case, which is the roadblock. The simulator will simulate the echo signal within the digital twin and give feedback to the tag optimizer. The MetaWave tag optimizer fine-tunes the tag parameter until it makes the victim's mmWave sensor makes a mistake. We here evaluate the MetaWave's ability to attack range, angle, and the speed measurement in real practice. The average success rate is 97%, 96%, and 91% respectively. And here are examples for real-world attack at different location, weather condition, and time of day. The top two are attacking the range measurement in collision avoidance and intruder detection scenario. As you can see, the MetaWave tag with the MetaWave tag, we can successfully disappear the rock and the intruder. On the bottom left is attacking the sensor the angle measurement, which we put a MetaWave tag on the side of the road, and make the sensor results believe the human in the front of the car is also on the side of the road. We also want attacking the speed measurement, where we deploy the tag using a drone, and we are able to generate a huge turbulence in the speed measurement results. MetaWave is also capable of perform multi-object attack. As shown in this figure, we can choose to hide the subject 2, who is wearing the MetaWave tag from the radar measurement result, while keeping the trajectory of the subject 1. We also evaluated our simulator directly comparing the simulated signal with the real-world signal. The result shows our simulator is capable of simulating the echo signal with and without the MetaWave tag. And then I will talk about the countermeasures. The traditional measures are based on the human inspection. Since the millimeter wave has the ability to sense non-line of sight, so we can camouflage the tag to blend in the surrounding environment. As shown in the image on the left, the tag is made into a for rent road sign, which make this kind of camouflage can make the tag more stealthy. Furthermore, since there are no electronic components on our MetaWave tag, it's there, so it cannot be detected by radiation detector. There are also some emerging countermeasures. Fingerprinting, RF fingerprinting utilizes a unique physical characteristic of the sensor component to judge if the received signal comes from the same electronic instrument. This can be used to detect the malicious signal. However, it's ineffective to MetaWave because MetaWave directly attacks the sensing signal from the original millimeter wave sensor. The constant false alarm rate technology is used to use the dynamic threshold to rule out the active or passive noise. However, we directly utilize the metamaterial tags to change the echo signal along with the environment. Thus, the false alarm detection cannot resist our attacks as well. It is possible for some device to employ different millimeter wave sensor operating under different setting frequency. However, MetaWave attacks are effective over a wide range of sensing frequencies simultaneously. Therefore, it's not very likely to work as well. To conclude, we propose a new passive attack type with metamaterial enhanced tags, millimeter wave sensing, and investigate the feasibility of these security threats. We designed and developed the first low-cost and easily obtainable metamaterial enhanced tags for millimeter wave ghost and vanish attack. We then design and implement a simulator-based MetaWave attack framework to optimize the attack. It can be enable stealthy and viable attack that rapidly analyze the physical environment and generates MetaWave tag design for the trap setup. That's all my presentation, and I'm happy to take any question.
Do you know if any card this AEV is wave sensing?
So what? That's manually just by their reusing
that I mean, just they will use the. Have you tried just the commercial way? You tried OBS, which we it's a commercial on free hair fountain transaction. So, do you know if AEB is implemented only using radar? Because I think if you're using radar only for AEB, then you're going to have too much to use.
With the also consider TRR. First question, I do not know their is only using video based radar, but we also consider the scenario of the JR
the system used the motion that illusion. And our test shows that we have a training camera and we can be at the same time. You speed up the kind of algorithm based on adverse or image. I'll show the difference. Another.
I'm guessing wondering how large of a tank you need to use to, for example, to perform a vanishing tank. That's the screen that you showed. Here, the entire sign was part of the material. Like, can you put a small patch on something and make it disappear?
Oh yeah, we also actually put all the translated dots. We can see that the paper the size of the tank is huge. So we can better disappear. It's only about our 30 to some fixed percent of the urban parameter or good cross section. The real cross section. Yeah, that's true. Another area of application for mmWave sensing are airport security scammers. Have you considered looking at whether a bad guy could make a knife or a button disappear and he goes through that scanner?
Yeah, sure. We actually do that after we has the R paper. Our simulator is for arbitrary type of objects with arbitrary with straight on. I believe it's definitely possible.
Questions?
That's a good reward things. I just have a follow-up question to the previous one regarding the size of the tag. So it seems that the tag is much smaller than the abstract code. So I'm really curious how the sort the simple reflected from a real tag.
Ordinal codes for different objects with geometry. The response single actually dominate for the few RF channel. So we could just go using the simulator to find the base, we are the dominant. And we could check outside the dot will with the overall amplitude below the detection threat and we'll see all that is here.
All right, thanks.